So I came across this problem recently, and since it was an interesting problem, I thought I would solve it and share it uh, with you guys as well. The problem statement is that the spectra of two stars shows a peak wavelength of roughly lambda 1 equals 1050 nanometers and lambda 2 equals 450 nanometers. The photometry of the star yields an apparent magnitude of 5.97 with a bolometric correction of 2.94. Similarly, photometry of the star 2 yields an apparent magnitude of 11.67 with a bolometric magnitude of 0.04. The parallax of both stars is 1.22 milliarc seconds, MAS, which is milliarc seconds, so like a thousandth of an arc second. So what it says is that calculate the bolometric luminosity in the solar units, the temperature of the both stars, and the radius of the stars in solar units. Assume zero interstellar extinction. To determine the luminosity of the star, we can use the Stephan-Boltzmann law, which is written over here. L star equals to 4 pi r star square sigma sp t star to the power 4, where sigma sp is the constant and the value for that constant is given over here as well. So if you look over here, we can see that we do not have the value for r, we do not have the value for t, and we do not have the value for L as well. All these three values are required for us to find. What do? We look at the peak wavelengths for each stars, lambda 1 and lambda 2, and we can determine the temperature for the stars using Wien's law. So this is the Wien's displacement law. Lambda max, the emission peak wavelength, is equal to some constant b divided by its temperature. So this is the value for the Wien's displacement constant, 2.8977 into 10 to the power minus 3 meter Kelvin. Now this can be rearranged to get the value for the star. So if we arrange the equation for Wien's displacement law for the temperature of the star, we get this equation over here. So now we can get the temperature from here. Okay, so now that we have temperature, we need to find the other two values, that are the radius and the luminosity of the star. To determine the value for the luminosity of the star, we come back here for the apparent magnitude of the star. So let's first do the relationship for the apparent and absolute magnitude. So the relationship between apparent and absolute magnitude is something like this, where capital M is the absolute magnitude of the star in V band. Similarly, the smaller m is the apparent magnitude. But here we notice that we need the distance to the star in parsecs as well, which we do not have, but fortunately we do have the parallax for both of these stars. So we can use parallax to get the distance to the stars. So we do that using this particular formula, which states that the distance to an object is equal to 1 over tangent of the measurement of the angular measurement in arc seconds. And since in arc seconds the values are really small, so that can be an approximation to 1 over parallax in arc seconds. So we have the parallax value as 1.22 milliarc seconds, so we can do that and put the value for d over here, put the value for parallax over here and get our value for d, and then we can put the d value over here in parsecs to get the value for the absolute magnitude. Okay, so now that we have the value for absolute magnitude, we would like to convert it into the bolometric magnitude, since we are given that the luminosity should be calculated in bolometric units. So for that we need the bolometric correction, which has been provided for both of these stars. So this is the formula for bolometric corrections. We get the bolometric magnitude by adding the bolometric correction to the absolute magnitude in the band. So now that we have the bolometric magnitude, now we can finally go towards the luminosity of the star. So now we get to this formula finally, that the luminosity of the star is equals to L naught 10 to the minus 0.4 bolometric luminosity of the star minus bolometric luminosity of the sun. So if we take the L naught value as the solar luminosity, then we can get the values back in solar luminosity, And we can also use the value for bolometric magnitude of sun, that is 4.75. So now we also have the formula for luminosity of the star, and now we just need to get the values for the temperature of the star and luminosity of the star, so that we can finally put all these values in this equation to get the value for radius of the star. So here we have the values for the first star that we are going to do calculations for. We have the peak wavelength, the apparent magnitude at 5.97, bolometric correction at 2.94, and parallax at 1.22 milliarc seconds. So the distance to the star comes out to be 819.67 to 1 parsecs, which is quite far away actually. So let's move on to the absolute magnitude of the star. Okay, so now we have the absolute magnitude of the star 1 in V band as well, which comes out to be negative 3.598. So let's do the bolometric correction, and now we have the bolometric magnitude for star 1 as well, which comes out to be negative 0.658. Okay, so we have determined the luminosity of the star in solar luminosity units as 145.614 solar luminosities. Now that we have the luminosity of the star, let's find out the temperature of the star. So for the temperature, we use the Wien's displacement law. We plug in the value for B and lambda max. I've changed the value for B into micrometers Kelvin, and also I've changed the value for lambda max from nanometers to micrometers. So the temperature comes out to be 19,320 kelvins. Okay, now that we have the luminosity of the star and the temperature of the star, let's find out the radius of the star. So using these values that we obtained, 145.614 solar luminosity and 19,320 kelvins of temperature, we get the radius of the star as 1.082 solar radius. So slightly larger than the sun, but obviously like almost 3 times hotter and 145 times more luminous than our sun. We can do this procedure, whole procedure for the second star as well, and then we'll get the value for the luminosity, radius and temperature for star 2 as well. Okay, so now we have done that for star 2 as well. So for star 2 we had 450 nanometers of lambda max, 11.67 as the apparent V band magnitude, the bolometric correction was 0.04, and the parallax was obviously 1.22 milliarc second. So the distance remains the same, 819 parsecs. The absolute magnitude comes out to be 2.102, and the bolometric magnitude comes out to be 2.142, and so the luminosity value is 11.046, which is like a lot less than star 1. And then we have the temperature of 6440, which is roughly I guess which is 1.11 times the solar temperature. And then we put these values into the Stefan-Boltzmann equation to get the radius of the star, which comes out to be 2.6823. So star 2 is slightly bigger, but the luminosity of the star is less and the temperature is also closer to the solar value. However, for the star 1, we see that the radius of the star is almost the same as the sun. However, the temperature and the luminosity of the star is quite huge when compared to the solar values. So this was so these are the values for the luminosity, temperature and the radius of the star. Hope you liked the video and hope you learned from it as well. Thank you for watching.